Harish, Mani
Sir,
Kumar,
చెప్పండి సార్.
Ravi,
Fine,
anyone
sir.
call? Yeah. Slide కనిపిస్తుందా? Are you seeing slide?
Confusing, sir.
Okay.
ఓకే సార్.
1 and 2, process 1 and 2. See, this is the pumping process. Understand? And 2 to 3 is the constant pressure heat addition. Constant pressure heat addition. And 3 to 4 is the isentropic expansion. And 4 to 1 is the constant pressure heat rejection. See, we can put the state points at anywhere. Understand? From here also we can start 1, 2, 3, 4, 5 like this. If you select thermal engineering by Rajput, that author mentioned state point 1 here. Understand? Here, expansion after the expansion. Process 3 to 4 is the expansion, isentropic expansion process. H3 minus H4. H3 minus H4 is the turbine work input. Got it? And why sorry falling? H2, HF2 minus HF1 will be give the this pump work process. Got it? H3 minus H2. H3 minus H2 will be the constant pressure heat addition, and H4 minus or HF4 minus HF1. This is the heat rejection to the condenser. Understand? Don't worry about the state points, but in which process we are adding the heat, in which process heat is, work done is producing, in which process heat is rejecting, and in which process work is supplying to the system. Understand? This is the expansion process. In this process, work done will be produced. H3 minus H4 is the work done. Okay. H3 minus HF1 is the heat supplied. HF4 minus HF1 is the heat rejected, and HF2 minus HF1 is the pump work. Understand? And come for the next cycle, next slide. Concentrate on one. So what is the required data? Enthalpy difference between the state points H3 minus HF4, which corresponds to the turbine work. Okay. So he mentioned one. Since we do not know the exact vapor quality of the outlet stream, we have to determine this parameter. Stage 4 is fixed by the pressure P4, 0.008 megapascal. This value is given in the problem. Understand? And the fact that specific entropy is constant, because this is the isentropic expansion process. S3 is equal to SF4. Understand? And can be picked from the steam tables. In previous class we discussed the method of taking or picking the values from steam tables. Okay, in this case, wet steam, the actual entropy can be calculated vapor quality X. Okay, SF4 is equal to SVX plus 1 minus X into SI, where S4 is enthalpy of the wet steam, 5.89 kilojoules per kg degree K. How can we can select this corresponding to this P4 value? Okay, if you see the steam tables, entropy S4 can be taken from steam tables at 0.008 bar or megapascal. Understand? And SV is entropy of dry steam, 8.222 kilojoules per kg degree K. Yeah. Understand? 0.008 megapascal. What will be the entropy of the dry steam? SG. We can take it as a SG. And SI, entropy of the liquid. Okay. In steam tables, this is represented with SF. Okay. If you observe the steam tables, what is the terminology? VF, VG, HG, HF, HFG, SF, SFG, SG. These terms we can see. V stands for specific volume. VF stands for specific volume of the liquid. VG stands for specific volume of the vapor. HG stands for specific enthalpy of vapor or gas or steam. Yeah, HF means enthalpy of the liquid. HFG means latent heat of vaporization. SF means entropy of specific entropy of the liquid. SG means specific entropy of the vapor or gas or steam. SFG means entropy of evaporation. Okay, all these values will be taken from steam tables. From this equation, what is this? SF4 is equal to SFV into x plus 1 minus x. In thermodynamics, we selected another formula also. S4 is equal to S4 is equal to S3. Got it? Or S3 is equal to SF4. S3 means the pressure at a given pressure. What is the inlet pressure to the turbine? What is inlet pressure given in the problem? Huh? Let us see. What is the inlet pressure? 6 megapascal. 6 megapascal is the inlet pressure. Okay. That S3 is equal to SF4. SF4 can also be calculated as SF plus X into SFG. Likewise, we can calculate. From this, we can calculate. See, here, this is based on that, we can calculate because that is the isentropic expansion process. Without using that also, we can calculate S4, V into X plus 1 minus X into SL. If you simplify it, we can get X4 is equal to S4 minus SL by SL minus S. Are you seeing? 5.89, 0.592 by 8.227 minus 0.592. Okay, if you substitute all the values, in that expression, we will get that x4 as 0.694.
సార్
Okay, boys, are you seeing? Hello?
కనిపించడం లేదు కనిపించడం లేదు సార్.
అంత వైట్ గా కనిపిస్తుందా?
అవును సార్,
స్లైడ్ కనిపించట్లేదా?
కనపడుతుంది సార్.
కనిపించడం లేదు సార్. కనిపించడం లేదు సార్, వైట్ గా కనిపిస్తుంది సార్.
టెక్స్ట్ కనిపించట్లేదా? ఎవరికి కనిపించట్లేదా?
కనిపిస్తుంది సార్.
కనిపించడం లేదు సార్.
కనిపిస్తుంది సార్.
ఓకే బాబు, ఎవరికైతే ఒకవేళ కనపడకపోతే అది మన మొబైల్ ప్రాబ్లం ఏమో చూడండి అమ్మా.
మొబైల్ ప్రాబ్లం
ఎందుకంటే ఇక్కడ కొంతమంది కనిపిస్తుంది కాబట్టి ఎవరికైతే కనిపించట్లేదు అది మొబైల్ ప్రాబ్లం ఉండొచ్చు, స్క్రీన్ ప్రాబ్లం. ఓకే, అండ్ కమ్ ఫర్ నెక్స్ట్ స్లైడ్. What is the second data, second required data? The enthalpy of the state 3 can be picked directly from the steam tables, whereas the enthalpy for the state 4 must be calculated using vapor quality. H3 at 6 megapascal, enthalpy value is 2785. Directly we can calculate it. And H thus can be calculated as H4x plus 1 minus x into HL. Got it? 2576. Okay. Point x value, whatever the value, dryness fraction we got 0.694 plus 1 minus 0.694 into 1.174. So if we multiply it and simplify, we will get H4 value as 1840 kilojoules per kg. Then the work done by the steam turbine is equal to the delta H, that is enthalpy difference, H3 minus H4. Here you can see H3 comma V. He is mentioning V. What is the meaning of that V? That is the meaning of pure steam, Hg, dry and saturated steam. Okay, after expansion, dryness fraction will be reduced. That is why we mentioning wet steam, H4. Okay, that too, what is the X4 value? 0.694. 694 is the dryness steam, dryness fraction or quality of the steam. Okay, if you consider the enthalpy difference, H3 minus H4, that will be the work done by the turbine. Okay, what is the next problem? That is next data 3. Enthalpy of state 1 can be directly fixed from steam tables. We have taken 1, state 1, because how can we take that value directly taken? Anyone? H1. See boys, go for the line diagram. Line diagram. H1. This is the go. H4. H4 and S1. What is asking? If this enthalpy difference will be the heat rejected to the cooling water, and H2 minus H1 will be the work supplied to the pump. Okay. Mm. Since state 2 is fixed by the pressure P2, 0.6 megapascal, and fact that specific entropy is constant for the isentropic compression, S1 is equal to S2. Cut it. That is a isentropic compression. Pump is using isentropic. See here, you may get a, turbine. Turbine pressure is at 6 megapascal. Okay, but pump is applying the feed water to the boiler at 0.6.0 megapascal. Okay, that is the constant pressure heat addition to 3A 3. Entire this process is the constant pressure heat addition process. Being it is isentropic compression, S1 is equal to S2. Okay, we calculated S2 value as 0.592. Directly we can take pressure 0.008 megapascal. So at this, for this S2 is equal to 0.592 kilojoules per kg degree K, and the P2 value given 6 megapascal. So corresponding H2 value will be taken from steam tables. So that value is 179.2. Boys, here you are seeing subcooled. Subcooled. Hello? Ravi? You are recording this meeting. Uh, some very disturbances are coming. Wait. Don't go, boys. 1 minute. Mm. Okay. Mm. Now are you seeing now? Boys.
Yes, sir.
ఇప్పుడు కనిపిస్తుందా కొంచెం క్లియర్గా?
కనిపిస్తుంది సార్. ఎస్ సార్.
ఓకే. కొంచెం ఇప్పుడు enthalpy for state 1 can be picked directly from steam tables. H1L, this L indicates liquid. Okay, liquid enthalpy H1 at a given pressure is 174 kilojoules per kg. Stage 2 is fixed by the pressure P2, 6 megapascal, because that entire line is on constant pressure line, and fact that specific entropy is constant for the isentropic compression. S1 is equal to S2, that is equal to 0.592 kilojoules per kg degree K. For that given pressure 0.008 megapascal. For this entropy, S2 is equal to 0.592. This is also directly taken value at 6 megapascal. SF2 value, that is okay. S2 value at P2, and we find H2, that is nothing but HF2 in steam tables. Understand? So at that 6 megapascal pressure, HF2 is equal to 179.7 kilojoules per kg. Okay, therefore the pump required by the pump WP is equal to delta H. Got it? So are you following? 179 H2 minus H1. 179.7 minus 174. If we calculate it, we will get 5.7 kilojoules per kg. This is nothing but pump work done by the pump. And what is the fourth required data? Enthalpy difference between stage 2 to 3. This is nothing but heat addition to the stream at constant pressure. Okay, Q added, this is nothing but heat supplied. H3V, this is nothing but enthalpy of the steam at boiler outlet or turbine inlet, minus HF2, subcooled means liquid, HF2. So H3 value directly taken, Hg value at 6 megapascal, 2785, minus 179.7. H2, HF2, this is nothing but HF2 value at pressure which at which pump is operating. And note that there is no heat regeneration in this cycle. The problem he mentioned, there is no heat regeneration. That is why we mentioning it. On the other hand, most of the heat added is for the enthalpy of the vaporization. Okay, heat supplied is equal to 2605 0.3 kilojoules. What is the next fifth one? In this case, we are considering both the Carnot efficiency and the Rankine cycle efficiency. We are comparing both. Okay, from second law of thermodynamics, Carnot efficiency is equal to 1 minus uh, cold fluid temperature by hot fluid temperature, or 1 minus TL temperature at lower temperature body by T hot temperature body. This given 1 minus 315 by 549. All these values are given in the problem. So what is the Carnot efficiency? 42.6 percentage, or in points value 0.426 will come. Once we multiply it with 100, we will get 42.6. Here where the temperature of hot reservoir is, where we got these values means 275 degrees centigrade. That is given in centigrade. To convert it, we have to add 273 degrees centigrade. Temperature of the cold reservoir is it 41.5 degrees centigrade. If you completely add 273 degrees, it will come like this. Okay, these are the values we got. Approximately 548, 548.7 is treated as a 549, and 314.7 degree Kelvin is rounded as 315 degrees centigrade. Okay, now the thermodynamic cycle efficiency of the uh, Rankine cycle can also be calculated by the formula. What is it? Tell me. Turbine work output minus pump work by heat supplied. If you do this, turbine work we got 945 kilojoules per kg degree K. What is the pump work? 5.7 kilojoules per kg degree K. So what is the heat supplied? 2605.3. So if we calculate it or simplify it, we will get 36.1 percentage. Here, what is the thing we found? Carnot efficiency is very much higher than Rankine cycle efficiency. Okay, Carnot cycle is the ideal cycle. Carnot cycle is the ideal cycle. Okay. Remaining cycles are all actual cycles. So actual cycle efficiency is always less than the ideal cycle efficiencies. Okay, once again recall the problem. Okay, boys, go for the first slide. There's a problem side. Problem. All of you see the first slide. Here, what is the thing you have to concentrate? What is the pressure of the steam at which turbine is operating? First thing. In this case, the turbine operates at a pressure of 6 megapascal and saturation temperature 275 degrees centigrade. Okay, and X is equal to 1. Cut it. He mentioned dry and saturated steam. He mentioned. Okay, what is the state point 3? State point number 3 he mentioned. So at 6 megapascal or 6 bar, we have to calculate enthalpy of the steam, H3. This is the H3 value. Okay, from steam tables we can directly take these values. Got it? And turbine exit pressure is 0.008 megapascal. 0.008 megapascal. Steam leaves the stage of turbine at a pressure of 0.008 megapascal. See, state point 4. Understand? H of 4 will be taken directly from the steam tables at this 0.008 bar and 41.5 degree centigrade. Understand? We have P3 value. Understand? So H3 value can be calculated. We have P4 value, and we can take HF4 value. Okay, 3 to 4 is the isentropic expansion. So directly we can take the value S3 from steam tables, and we can calculate S4, okay, as SF4 plus X4 into SFG. Like this we can calculate, or SF4X plus 1 minus X into SF. In this formula can also be used in thermodynamics. Properties of the pure steam, we you can recall it. Okay, then after come for the uh, next thing, next slide. And all the entire this is the given the required data. By using required data, sorry, given data with appropriate formulas, we can find out the given values. Okay, you can see this is the Rankine cycle. 3 to 4 expansion process, 4 to 1 heat rejection process, 1 to 2 compression process, 2 3 3 heat addition at a constant pressure process. Okay, are you following? Once we refer the steam tables, then we will easily understand it. If not, is slight difficulty and confusion with this. Understand? We have to always follow the steam tables while we are solving the problems. Okay. Any doubt? Hello? Hello?
చెప్పండి సార్.
ఎవరికైనా డౌట్ ఉంటే అడగండి అమ్మా. You can ask me. Boys, if you have thermodynamics textbooks, you can refer the problem for Rankine cycle also. Okay. What do you say? Hello, Ravi.
సార్.
Are you following?
ఎస్ సార్.
See, at beginning it may be slightly inconvenience and a difficulty, a little bit fear may be there. Understand? But by solving the problems one by one at your homes, you will become very familiar with that terminology, how to pick up the values from the steam tables, what sort of problems we have to use to calculate required data with help of given data and appropriate formulas. Got it? um, Learn the formulas very keenly. That is why every class I am asking and requesting all the students to refer the textbooks. Okay.
ఓకే సార్.
Tomorrow we will come with another session. Okay.
ఓకే సార్.
Thank you very much. You can leave now. Bye.